There are a number of ways using which we can estimate the value of pi using Monte Carlo simulations. Today we will estimate the value of pi using one such method. Okay, let's assume we have a square. Okay, we have this square with side uh, in some units 2, let's say 2 meters, right? So we have a square with side 2 meters. The origin is at the center of the square. So we have 1 and 1. So the square side is 2 meters. Now let's say we have a circle inside the square. So the circle edges touching the square edges at these 4 corners, right? So which means the radius of the circle is half of the length of the square, right? So the circle radius is equals to 1. The length of the square or the side is equals to 2 in some arbitrary units. Okay, now we are going to drop some points from the top. So imagine this is on the ground. Let's say some rain is falling, or we are dropping some points from the top. Now first we ask the question, what is the probability that the raindrop lies within the circle? Okay, that's question number 1. And after we find that, we will see how we can estimate the value of pi using that probability. Okay, again, to quickly summarize the problem, we have a square of side 2 meters. Then we have a circle inside the square of radius 1 meter. So we are dropping some raindrops from the top. Now they can fall anywhere within the square, right? Sometimes inside the circle, sometimes outside the circle, but still within the square. Now we are asking the question, what is the probability that the raindrop fall within the circle? After we find out answer to that question, then we will find out how we can estimate the value of pi. Okay, all right. So let's say we are going to drop some 100,000 raindrops. Okay, 100,000 raindrops are points. Now we want to generate 100,000 coordinates, x and y, right? So 2 numbers for each point. We have x and y coordinates, and they should lie between -1 to +1. So both the x and y should lie between -1 to +1. Okay, so here we are using a uniform random number generator. So the value should be between -1 to +1, and number of such numbers is equals to the number of drops, which is let's say 100,000 in this case, right? So we have generated 100,000 x values and 100,000 y values, right? So the first value in x, the first value in y corresponds to a point on this plane within this square, right? So if you look at the first 10 values of the x, they look like this, right? So they are between -1 to +1 with equal probability. Now we know the coordinates, and now we want to find out if the coordinate or the point is within the circle or not. Now how do we find that? For example, let's take this point, right? So somewhere this point. Now if it lies within the circle, here is the origin. It's x square plus y squared. This distance should be less than the radius of the circle, right? If it is greater than the radius of the circle, that means the point is outside this circle. Okay, so what do we do is, for every point we have generated, we compute x squared plus y squared, right? Because the origin is at the center. So x squared plus y squared gives us the distance of the point from the center of the square or the circle, right? So the center of the square and the center of the circle, they coincide, right? So x square plus y square give this distance. If it is greater than 1, that means the point lies outside the circle. If it is less than 1, the point lies inside the circle. Okay, so here what we did is, we are checking if it lies inside the circle, meaning the distance is less than 1 or not, right? So is inside, this is going to be again a list of size same as the number of drops, but it will contain false and true like that, right? So true means that the point lies inside the circle. False means the point lies outside the circle. Okay. So here is inside. We are just computing how many trues are there by using a numpy sum. So this false is represented as 0 and true is represented as 1 when we do the sum. So all trues are counted and the number of points lying inside is roughly about 78,000. Okay. So if we measure the probability, so the total number of drops, we have done 100,000 drops, and among which 78,000 of them have fallen inside the circle. That means the probability of dropping inside the circle is roughly 78,000 divided with 100,000, which is 0.78. So the probability of dropping a point inside the circle is 0.78. Now, let's try to understand, let's try to build some intuition, right? Now, the probability of dropping inside the circle will be high if the circle area is high compared to the square area, right? For example, instead of having this big circle, let's imagine a small circle here, right? Then the probability would be low. Okay. So the probability is simply the ratio of the circle, the area of the circle divided with the area of the square. Okay. So for example, here, the probability of the point dropping inside is equals to the area of the circle divided with the area of the square, right? So the bigger the area of the circle compared to the area of the square, the higher the probability. Okay. Of course, the circle area won't be greater than the square area because this is the maximum circle we can fit inside the square. Okay. All right. So in our case, we have, so the circle area is pi r square, pi. We have the radius 1. So it's 1 times 1. That's the area of the circle. And then area of the square is 2 times 2 because the side is 2 units, right? So this means the probability of dropping inside is equals to pi divided with the 4. Okay, which means pi value will be equal to 4 times the probability of dropping inside. Okay, so here we have the circle radius 1, the square side 2. Here we have computed the circle area and then the square area. All right. So the pi value is equals to 4 times the probability of inside. We have already computed the probability of inside, which is about 0.78. So if you multiply 4 with 0.78, we get this measured probability of our estimated probability 3.14, whereas the actual probability is also 3.14515. So these two are very close. Now, as we increase the number of points, I mean, in this case, we have done 100,000, but as we increase the number of points, this value gets even closer to the true value. Okay. Now let's do with very few points so that you can see how they are falling. So let's say we are dropping only 100 points. You see the 100 points, they are like here. It is even hard to see the square and the circular shapes, right? As we increase more and more points, we have more points on the edge so that we can see where the circle stops. Okay, so let's increase the number of points to maybe 10,000, which is 10 times less than what we saw initially. So here we can see the circle. So out of those 10,000 points, roughly about 79,000 points, they have fallen inside the circle. The remaining 2,100 points, they are at these 4 edges. Okay. Now the pi value is 3.16. Earlier we got 3.14, right? So as we increase the number of points, we get closer and closer to the actual pi value. So here we got 3.1139, which is close to 3.14. Okay. Now here we are just plotting, we are just color coding the points which are inside the circle. So here what we did is X inside. So X contain all the, let's say, 100,000 points, and then we are filtering using the Boolean, is it inside? So is inside has values true and false, right? So only when it is true, those values get copied into X inside and the corresponding Y values. And here we just set the size because it is a square. We set equal dimensions in the X and Y direction. Now here we are plotting all the 100,000 points. So if we disable this, that will be all the 100,000 points. And then those, and here we are plotting those points which fall inside the circle. So using this green color. Okay, so that's why we can clearly see the circle shape. That's all for today. As I said, there are many ways we can estimate pi using Monte Carlo simulations. Maybe we will look at a couple of different ways in the future videos. That's all for today. Thank you very much.